So, Jason, we all know all the PQC algorithms now, don't we?
Let me
There's
try to rhyme them
several
off.
DSAs,
Yes.
and everybody knows there's only one chem, right?
There's another.
Wrong. That's right. So
another.
ML Chem, everybody knows ML Chem. However, there's another was chosen.
Yeah,
Another
recently.
of the round 4 candidates, HQC.
HQC. Hey, and we're starting to get some diversity in math now as well.
Yep.
Because it's code based.
And that's the point. That's the entire point of it, right? Is diversity in math. So go on. It's code-based.
So great. Another chem.
Yep.
Well, we needed it.
Yep.
We needed it because there was just the one.
They have some eggs in a different basket.
Can't call it diversity if there's one.
Yeah. Yeah.
So we got two, and it was what is it? It was one of the original submissions.
Yeah. It was all the way back to the very beginning.
First
it was
round.
an original round 1. It went through. It lived on in round 4 after the winners were chosen. The round 3 winners were chosen, and it spat out, I think, in March of this year. I think it was. NIST announced that it is another approved algorithm.
Right on.
So we don't have our FIPS yet, but surely that's on the way.
Tim, here's what I'm going to give you. Every once in a while, I like to give the intuitive explanation.
Great.
For why is it hard for a quantum computer to solve the underlying math?
Yes.
Because I love how you can say it quickly. Anybody who's involved in this industry can say that RSA is based on the difficulty of solving for large prime numbers. Mm-hmm. Boom. And it's kind of, as long as you understand a little bit of number theory, it becomes intuitive.
Yep.
You understand why it's hard for a normal computer. ECC, a little more difficult to explain, but it's based on geometry. Mm-hmm. Okay. We've done this in the past with lattice and, shortest vector problem, right?
Yep.
I want to back up just for a second before I explain HQC and say, where a quantum computer is awesome and can break things is when there is periodicity. In other words, there's a pattern to, when things show up in time and space.
Okay.
And this is the thing about prime numbers is that it's kind of quasi-random, not proven to be anything but yet in number theory. And that's what makes it so incredibly hard for a normal classical computer to break RSA, especially when you get into really large prime numbers. But a quantum computer with Shor's algorithm can defeat it because there kind of is, a periodicity to it in a sense, right? But enough about that. It helps to give you an intuitive understanding of this factorization and periodicity of patterns that quantum computers are so darn good at. But they're not great when things are really, really random. And what I mean by random is this: codes-based cryptographic algorithms, of which HQC is one. Think about this for a second. If I gave you a public key that, and here's the analogy, and all of you guys who are like the mathematicians in the room, don't throw eggs. This is me just trying to have fun and explain it intuitively. Your public key, think of it as like, you remember back in the day, Tim, where sometimes you turn on a television, you see just noise, white noise, and you hear the static.
Yep.
And the reasons for that are interesting. We could have whole podcasts on what that static actually is. But what happens if you took that kind of just super duper random static image and video, and you started to put in almost like steganography, actual information is embedded. But if somebody were looking over your shoulder,
in a way that you wouldn't perceive it.
If somebody were looking over your shoulder right at that public key, somebody was given the data. Somebody was it was completely public, which a public key should be. Mm-hmm. There should be no way at all to discern what the actual signal is, the actual information, the imprinted code information into this static electricity type of signal. And so the private key is essentially, here's how to get rid of the noise.
Okay.
That's the private key. And it makes sense because the public key can be looked at by anybody. And it's like, how do I interpret this? Well, unless you have the private key, you can't decode it. And that's what code-based cryptography is about. It's about putting solid signals into absolutely horrendously difficult noise. And the private key being a very
Way to
fast,
extract that signal.
a very, very fast way of extracting it. Essentially, how to remove the noise. And so that's about as intuitive as I can get in explaining that one. Obviously, vastly, vastly oversimplified, so don't throw eggs. But it's a fun thought.
Sure. And it's the second chem, like we said.
Yeah.
I still feel like all the momentum's behind ML Chem. I think we're going to want to think of this as an emergency, in case of emergency, break glass kind of situation.
Yeah. And also, Tim, I think we should have a second podcast on HQC to talk about when would you use ML Chem versus HQC, because I think there's some insights as to which use cases might favor one or the other.
Okay. All right. Well, that's interesting.
Yeah.
All right. Thank you, Jason.
Thank you, Tim.